I'm going to go over problem number 18 in WeBWorK 16, where you got to find the eigenvalues and eigenvectors of the given matrix, and then solve a system of differential equations given the set of initial conditions. So the first thing you would do is set the determinant of a minus lambda I equal to 0, in which you take the diagonal values down and subtract lambda from. And so taking the matrix of negative 11 minus lambda, negative 3, 6, and negative 2 minus lambda. Set that equal to 0, or we cross multiply. You're given the quantity negative 11 minus lambda times minus 2 minus lambda minus the negative 18. Negative 3 times 6, subtracting that, and set that equal to 0. Multiplying through, 22 plus 2 lambda plus 11 lambda plus lambda squared plus 18 equals 0. Simplifying and reordering, you get lambda squared plus 13 lambda plus 40 equals 0. Now, I don't believe that factors nicely. I could be wrong, but taking the quadratic formula will work nicely here. Lambda will equal minus 13 plus or minus the square root of 13 squared. Minus 4 times 1 times 40 divided by 2 times 1, which quickly reduces to negative 13 plus or minus the square root of 9. That would be 169 minus 160 divided by 2. Square root of 9 is 3, which will yield the lambda values of negative 16 over 2 and negative 10 over 2, or minus 8 and minus 5. So now, taking our lambda value, we'll take lambda 2 first. That's what I did first. And substitute the value in for lambda in our matrix. Negative 11 minus the negative 5, negative 3, 6, and negative 2 minus a negative 5, which would have our matrix of a negative 6, 6, negative 3, and 3, times our k1 vector, and set that equal to the 0 vector. So just taking the top half, multiplying it by the k1 vector, you get negative 6 k1 minus 3 k2 equals the 0 vector. Ignore that part. I don't know why I put that there, but you get negative 6 k1 equals 3 k2. Ignore that 0 vector. It shouldn't be there. Same thing here. I don't know what I was doing. Negative 2 k1 equals k2. That's just dividing by 3. So k1 will be our free variable, and k2 will be the dependent. So we can set k1 to what we want. We'll set it to 1 here. And then k2 will be equal to negative 2 times that, or times 1. And k2 will then equal negative 2, which would have our k1 vector as 1 and negative 2. And our x1 vector would equal 1, negative 2 times e to lambda t, or negative 5t in this case. Now taking our lambda 1 of negative 8, doing the same process over again. So substituting in negative 8 for lambda, we get the matrix of negative 3, 3, 6, and 6, multiplying that by the k2 vector, and setting it equal to the 0 vector. And it looks like this time I actually did it right. Negative 3 k1 minus 3 k2. Or that should be... Excuse me, let me backtrack for a second. The matrix should be negative 3, 6, and 6. So you get negative 3k1 minus the 3k2, which equals the 0 vector. And then negative 3k2 equals 3k1. That would be adding over 3k1 to the other side and getting rid of the 0 vector this time. Negative k2 equals k1. That's dividing by 3 from both sides. And now here the k1 or k2 would be the free variable. K1 will be dependent, so we set k2 equal to 1, and k1 simply equals negative the negative of k2, or negative 1, making our k2 vector 1, negative 1, and our x2 solution vector of 1, negative 1 times e to the lambda t, in this case lambda negative 8, so it'll be e to the negative 8t. And now that we have that, we can start solving the differential equation for the initial value problem. in which you're given on the problem you're given x1 of 0 and x2 of 0 equals -2, 1. That could also, in this case, and I will do it this way, x of 0 and y of 0 in the parametric solution curve. So what we have right now is x equals c1 times the x1 vector, which is that. So you get c1 times the x1 vector of e to the -5 plus c2, the x2 vector, e to the -8t. Y equals -2 c1 e to the -5t minus c2 e to the -8t. That would be the general solution curve. Now, solving for the IVP, x of 0, or taking the x of 0, substituting in 0 for t, you get c1 e to the 0, -5 times 0 being 0. So just get c1 plus c2 times e to the 0, or 1, equals -2. And y of 0 equals -2 c1 minus c2, again, e to the 0 being 0 on both of these, equals 1. And now we can make this a system, add them, cancel out the c2's, and solve for c1. So doing that, you get c1 minus 2c1, or -c1, c2 minus c2 being 0, those go away, and -2 plus 1 equals -1. Flipping the minus signs, c1 simply equals 1. And now we can take either one. I took the first one, and then substitute in the c1 value of 1, plus c2 equals -2, subtracting over 1, so yield c2 equals -3. And now we can take our c values, substitute them in, and get our final solution curve. In this case, the parametric form would be x equals e to the -5t minus 3e to the 8t, -8t, excuse me. And y equals -2 e to the -5t plus 3e to the -8t. And then in the y1, we have -2 times c1. That's where the -2 comes from. And that will do it. To quickly review, so to get the eigenvalues, set your determinant of a minus lambda I, or subtract lambda from the values on the diagonal, regardless of how big the matrix is. Set that equal to 0, cross multiply, solve for your lambda, values. Take each one, substitute lambda back into the matrix. Take the top one, multiply it through by the k1 vector or k2 vector. Solve for k1 and k2, and retrieve your k1 vector, and then get your x1 solution vector. And then you repeat for the second lambda value, get those. And then when you get to the initial value problem, you can get your parametric solution curve, the general version of it. Substitute in your given initial conditions. Solve for your c values, and then substitute them back in to get your final solution curve. Thank you for watching.